So in the class today, we're going to move to a slightly different topic to the ones we had seen previously. And we're going to talk about crawling and indexing today in the context of information retrieval. And information retrieval in general, we can have multimedia information retrieval, but the classical scenario for information retrieval is to do with managing text data. So managing text documents effectively. Which has become very important, in particular in the context of the web. So to speak a little bit about information retrieval, the context or the problem is that we have so much information nowadays available to us that it's very important to be able to find the information that we're looking for when we need it. If we don't have some techniques to help us find the information that we want when we want it, then the web would be a lot less useful. For example, if there were no search engines, it would become a lot more difficult to use the web. So, and this is because there's so much information available that it's almost as if there were no information available, right? If we didn't have search engines. So to kind of emphasize that point, there's this book by Borges, or this story, The Library of Babel. And in this Library of Babel, that Borges describes this library contains all books, possible books, with 25 unique characters, 80 characters per line, 40 lines per page, with 410 pages. So we can multiply the pages by the lines by the characters to get the length of the book in characters. And then to find out the total possible books, we have the number of unique characters to the power of the number of characters in each book. So we would have 25 to the power of 1.3 million books. So this library would not be feasible within our observable reality, let's say, within the observable universe. There's something like 10 to the power of 80 atoms, 10 to the 81, 10 to the 82 atoms, which is, and this number is far, far larger than that. So we could never possibly have all books. But as a sort of hypothetical library, it's sort of interesting for our purposes. So you would have every book imaginable, and you would even have a book that contains the location of all useful books. For example, the book that contains the cure for cancer or COVID-19 or what the meaning of life, whatever it might be. So the problem, or what this illustrates, is effectively this idea that all information is equal to zero information. If we had every possible string of length 1.3 million characters, it doesn't really offer any information for us. It's like, it's just, we could enumerate this. So the problem is actually, in terms of information, it's as important what is omitted as what is included, in a sense. If we were just given 5 or 10 books that were relevant, that would be far more useful to us than having this entire library of Babel at our to be able to access this library of Babel. It would be more useful if we were just given 5 or 10 interesting books. So this is sort of the overall concept of information retrieval. And in terms of the web, if we think about the book that indexes the library, okay, well, here we're talking about Google, and could also talk about Bing or some other search engine. So we can go here to find the information that we need when we need it. So we're going to talk a little bit about how Google works, and this will also be useful for other types of applications that have to deal with massive amounts of text documents. So speaking specifically about Google Web Search, the basic Google Web Search. So we spoke before about how Google implements its web search. We mentioned this in the context of the MapReduce class. So we mentioned that there are a number of processes, core processes like crawling, indexing, ranking, and there may also be other processes, but these are sort of the core 3 elements of building large-scale information retrieval systems, effectively search engines. So we're going to talk about crawling and indexing today, and the next time we're going to talk about ranking in more detail. So crawling relates to effectively navigating the web and extracting data from web pages. Indexing refers to taking the text content of those documents and inserting it into data structures that permit efficient lookups. Ranking refers to figuring out which documents are most relevant or which are the most probable documents that will be relevant to a user. And there may be other elements as well, other types of analytics and so forth that may be applied. These are the three core elements. Any questions? Okay, so if there's no questions, how does Google know about the web? Okay, so how does Google index large parts of the web? It has to somehow download or somehow copy content from the web into its indexes, right? So how does it do this? So it uses crawling. So the idea of crawling is to download the web, or at least parts of it. Okay, we can't download everything. So how does crawling work in general? In general, we're going to start with a list of seed URLs. These are URLs that are known before the crawl. If we want to crawl a particular website, for example, all the seed URLs will come from that website. But if we wanted to crawl the entire web, we might use some seed URLs from a previous crawl, for example. So we start by defining a frontier, which is essentially the frontier I will always be the list of URLs at step I that we want to crawl. So while this frontier is not empty, we're going to create a new frontier. And for each URL in the old frontier, we're going to download the page for that URL. And we're going to add all of the URLs from that page into the next frontier. So in every round, we're crawling all of the URLs, extracting the URLs, and adding them to the frontier, to the list of URLs that will be crawled in the next round. Okay. So here we're iterating round by round, and here we're iterating within each round over all the URLs for that round, adding the URLs found in this round to the next round, and storing the page or indexing it or whatever we'd like to do. And continuing then to the next round. So any ideas what we might be missing here? Or some problem that we might have with this process?
Possible loop.
Yep. So we might end up crawling the same pages. If page A links to page B and page B links to page A, then in frontier 1, let's say I starts with 1, we'll have A, and then frontier 2 will have B, and frontier 3 will have A, and frontier 4 will have B, and so forth. So we need to make sure that we don't enter into these cycles. So we'll need to somehow maintain some information about all the URLs that we've seen thus far. So we're going to now add this new set of seen URLs that we've seen during the crawl. And we're going to add these URLs. So we're going to add these URLs when we see them, and we're going to remove them from the frontier, or we can check to make sure that they're new before we add them to the frontier. So, okay, so we have to keep a global list of URLs that we've already visited, and then we continue on to the next round. So this avoids cycles, so we're not going to visit the same pages multiple times. In terms of the performance, what do you think would be the slowest part of this crawling right now? Which line or which part of the process would slow the crawl down? Any ideas?
Descargar la página.
Yep. Yeah. So downloading the page, because here we need to access the network. So this could potentially be quite a bottleneck. Quadratic over all pages It shouldn't be so long as we have our set here implements. If it had an n time, on time contains method, then it would be quadratic. But if we have here something that can do O1, for example, a hash set, or O log n, for example, a sorted set, then we do have more n log n, or even just on type performance. So we can avoid quadratic lookup as long as we have an efficient data structure here that allows an efficient contains. Well, I guess here, yeah, we could rewrite this so that it wouldn't be difficult to rewrite this to avoid quadratic. So the main issue would be the download page, the network. So what we'll need to do is somehow optimize that. Any ideas on how to optimize this, given that download page might take a long time? Okay, so let's have a look and see. This is slow because if we do pings, for example, if on my machine, if I try to ping Twitter, which is a very popular common website, just to send a message there, it takes 118 milliseconds. So it's considerably slower than reading something from the local disk or whatever. So this is just to establish a connection with Twitter. So this would become a bottleneck for the crawl. Any ideas of how to address that? Yep. So we can't really optimize crawling one page, right? But we can optimize crawling lots of pages by using threads. So if we're stuck waiting for a page to respond, our local machine that's doing the crawl is not doing anything. Its CPU is not being used. Its disk is not being used. So by using multiple threads and trying to contact to download several pages at once, we can have a much more efficient crawl, right? So the majority of time we'll be waiting for the connection. The disk CPU will be nearly zero, and also the bandwidth. I mean, while there's this ping delay, this latency, we're not really using the bandwidth. We're just waiting for a response. So the bandwidth as well will be underutilized. So multi-threading is important. So what we'll do is just rewrite our little pseudo code here. We still have our scene list, but instead of just downloading the page directly, we're going to have some sort of thread that can that will download the URLs. So it will it will accept the URLs that have been seen to avoid cycles, which will have to be synchronized, and the next frontier. So we'll extract the URLs, download this URL, extract its URLs, and add them to the frontier if they haven't already been seen, for example. And we'll keep a list of all these threads, and then we'll just pull them. So this is a very sort of basic crawler implementation. So here in the download page thread, what we're doing is downloading the page, checking to make sure that it hasn't been seen before. That doesn't make sense. I think probably that should, I don't know why you would download the page and then see if you've seen it before. Oh no, here it's removed anyways. Okay, yeah, so it's fine. So download the page, then you add it to the pages that have been downloaded, and then when you extract the URLs from the page, you remove the ones you've already seen and you store the page. These being synchronized, meaning that you don't want multiple threads to somehow to create inconsistent states in these data structures. So you don't want multiple threads reading and writing from those structures at the same time, for example, if they're not thread safe. So the core idea here is that using multi-threading, we can make the crawl a lot faster, okay? And so these were some experiments around at one time for something, some research paper, I think, which was, in any case, it was crawling 1,000 URLs on this particular machine. And it's a graph of how long it took to crawl 1,000 URLs. So we see that with one thread, it took about 30 minutes. With about 32 or 64 threads, it took a third of the time. So it's not, going to be 32 times faster, let's say, but it should be considerably faster. The exact figures here depends, like how many threads works is best and so forth. This really depends on a lot of details of the machine, the type of crawl you're doing, the bandwidth. It's very difficult. You would have to experimentally try an experiment like this to find an optimal number of threads. We see that as the number of threads goes, here's the percentage of CPU that's idle. So we see that with one thread, on average, the CPU, about 63–64% of the CPU is not being used. Whereas by using more threads, we get a better utilization of the local machine, where we have 20% idle or 80% of the CPU being used. So multi-threading is good. It's particularly good if you're crawling websites that have slow connections, or you have a slow connection, I guess. So, okay. So in the context of threads, it's a double-edged sword. So there is this concept of a denial of server attack, or a distributed denial of server attack, DOS or DDoS. And it's this idea of sending so many requests to a website that the web server can no longer process all of the requests and has to reject some of the requests. So essentially, these might be valid requests, where the client really wants the content requested, or it might be a deliberate attack on the website to send it so many requests that it has difficulty distinguishing the legitimate and illegitimate or attack requests. So there is this system, this tool you can download online called the Low Orbit Ion Cannon, which is basically what it's doing. He's just sending lots of requests to a website in multiple threads, and you can set how many threads you want and what website you want to attack. However, you have to be very careful about this, because this is considered in some cases, or in many cases, this would be considered illegal. So there is this famous case of Anonymous were organizing a denial of service attack against MasterCard with respect to them blocking donations to WikiLeaks. And a bunch of people used the tool I mentioned in the previous slide, including this guy who not only used the tool, he was also involved in organizing the DOS, but he ended up getting 18 months in prison for his role in this denial of service attack. So in the case of crawling, it's unlikely you're going to get imprisoned if you send too many requests accidentally while crawling, but it's much more likely that your IP range will be banned. So if you're in a university and you're crawling, you might end up, let's say you're crawling pages from, Google, you might end up getting your university banned from Google for a certain period of time, which has happened. Or maybe banned from Twitter or whatever you're crawling. So yeah, so we need to be careful. If too many requests are sent then to a website, then we might end up getting our IP range banned. So we need to consider this in the crawling. This assumes we're crawling multiple websites. What we can do is define here in the middle of our pseudocode as a scheduling function. And what the scheduler will try to do is it will try to maximize the time between two pages on one site. So if we have maybe 50 sites, it will try to interleave those sites so that we're not running like all of our requests on one site at a given moment. So without going into the details of what this does, just some function that will, in the list of URLs that we're going to download, it will try to keep some space between the two petitions to the same site. Okay, so and then we continue as usual, except for just that we'll try to space out requests to the one site. So, okay. With respect to how many requests is kind of typical, how do you know how many requests you can send to a website? There's some general rules of thumb. Some people say request every 10 seconds is fine because that's typical of what a human user would do. So, some people say a request every second should be okay as well. But it's hard to say. However, there is one way to know, which is in general, using the robots exclusion protocol, which more generally provides some guidelines to crawlers about crawling a certain website. So if you go to your favorite website and then do /robots.txt, you will very likely get some text file back And this text file will tell you some of what the owners of the website, the administrators, are requesting of their crawlers. So you can say, for example, user agent asterisk star disallow slash, and this basically says no bots are allowed on this website. So it basically bans all crawlers from the website. You can be more specific and say, okay, I don't want, I'd love for crawlers to access my homepage and all the stuff in my blogs and forums, but I don't want them in the user. Any URLs that have the user path or with main login, for example, I don't want these to be crawled. And this also would be respected by Google, which would then not crawl these or index these pages. Okay, and we can also ban a specific or reference a specific user agent. So when you send a HTTP request, you typically will send a user agent saying who you are. So for example, your browser will say, will give information about what browser you're using and so forth. Google will use the user agent Googlebot and its requests, HTTP requests. So you could just ban Google from crawling certain aspects of your website, certain parts of your website. There's also some non-standard extensions of robots. One of them that's of interest for the crawling is that we can specify a crawl delay. And this would say that we should only be able to crawl a page from this host no more than once every 10 seconds. So essentially, we should put a 10-second delay between sequential requests to the same website for this user agent in this specific case, but we can also set it for all if we wanted. Excuse me, there's also this extension which allows one to disallow everything and then afterwards just allow some specific things. So it's sort of like opt-in rather than opt-out. So rather than saying all the things you disallow, you can disallow everything and then you can just allow specific folders. Okay, so these are non-standard, but they're respected by many crawlers and many agents that are navigating the web. There's also a way to specify a sitemap.xml, which is an XML file that gives a bunch of links to your website. You can indicate which web pages you want crawl more frequently or less frequently, and you know, where are the entry points into your website. So these are all non-standard extensions. The important thing is that crawlers in general, they can't just do what they want. You know, there's some politeness is expected. Also, this robots.txt file allows website administrators to communicate to crawlers what is or isn't expected of them. There is absolutely no reason why a crawler, the crawler is not forced to respect the robots.txt. So, you know, you could ignore the robots.txt and just go ahead and crawl whatever you want and download it. But you could, it would be a basis for why you might be banned from making further your IP, or IP range might be banned from making further requests to that website, for example. So in general, it's good practice to follow this sort of protocol, because otherwise there's a good chance that you're going to get banned if you don't. Okay, so any questions or thoughts about that? Okay, so we can continue to the next question, which is, okay, we've considered crawling on one machine, but if we really wanted to scale out, we might consider using multiple machines, right? So how might we implement a distributed crawler? Here we assume we have five machines, right? And we're expecting similar benefits to multi-threading, in the sense that we'll be able to do more downloads in parallel. So how might we implement a distributed crawler? So what would be the complicated part? What would be the complicated parts of the process? Like we could just send, for example, you know, chunk or frontier list over the different machines randomly, and then have them crawl. Okay. So the difficult things would be the scene URLs. We need to somehow globally make sure that we're not repeating pages. And the other part would be the politeness. We want to maybe try to avoid sending lots of requests to the same site in a short space of time. So all of those things require coordination between machines. Otherwise, the machines can kind of more or less work independently. So what we could do is when we have our frontier, we can just map our frontier. We can use the URL of each frontier to map it to a particular machine, by which I mean take the hash of the URL modulo the number of machines. So we just partition essentially the URLs over the machine, and then each machine will be able to maintain just a local list, 1/5 of the scene list, because it knows that if that same URL is seen in the future, it will arrive to the same machine. We can also, for example, here we include the count of how many times that URL was seen, but that's not necessary. It could also be a 1, for example. So the main benefit or the main idea here would be to partition the URLs, okay? So that the same URL will always end up in the same machine, and each machine only needs to maintain a local scene list of URLs to avoid cycles. So what will be the bottleneck as the machines increase? As we add, let's say we had 500 machines, right? Will it be faster than having 5 machines? Will it be 100 times faster? Will it be 2 times faster? What does it depend on?
I think it depends on your capacity to write in memory.
To write in memory. So if you had potentially lots, let's say each had 10 gigabytes of memory, each of these 5 machines, and you have 50 gigabytes, you could assume that the 500 machines will have 5 terabytes of memory, for example. So let's imagine that the memory scales as well. So the memory is a local factor, right? But let's assume that you had the best possible hardware locally.
Okay, so the bottleneck should be the network.
Yeah. So it'll be the network coming into those machines. Yeah. So eventually you'll reach an issue where the bandwidth will become the problem. Another issue is that you have to wait so long. Essentially, you have too few websites, or the politeness days or delays are so long that you just end up having to wait a long time. For example, if you're waiting 10 seconds between each website, and you only have 10 websites that are active in the crawl, maybe you've crawled all the others already or something like that, then you can only do 1 request a second, right? So, and that has nothing to do with bandwidth, but just the fact that you have no choice. You have a sort of fixed budget of requests you can make to each website. So these external factors will become an issue, and this will limit somehow the performance as the number of machines grows. So at some point, it doesn't really make much sense to add more machines without adding more bandwidth, or maybe trying to do something with the politeness delays. Okay, so there is, as we've seen, many of the projects we've seen in the course come from the Apache software project. So there is an open source crawling framework called Apache Notch, and this is compatible with Hadoop. So it's specifically, you can use it within a Hadoop framework. As well, it's compatible with a tool that we'll see later called Lucene, specifically Solar. So it can index, both crawl and index content for you from the web. And it should have implemented robots.txt policies and so forth. So it's I would recommend, although it seems kind of easy to write crawlers, to hack together a crawler in Python or something like that, there's a lot of details that you have to think about when you start thinking about politeness, robots.txt, and so forth. So better to use an existing crawling framework. So that's briefly crawling. So it's sort of maybe a little bit of a side note to the course, which is focused on processing and analyzing lots of data, but oftentimes to get lots of data, or in projects relating to data intensive projects, you'll have to do some crawling or scraping of data from the web. So it's kind of a brief introduction of some things to consider when that happens. We won't have a lab on crawling because it's just too impractical to do. If you had 50 groups crawling the same website or whatever, it would have the IPs of the university would be banned. But it's useful to have some ideas of these concepts, the importance of multi-threading, the importance of politeness in particular, in mind. So that's crawling. Is there any question or doubt? Okay, so if there's no question or doubt about that, then we can move on to inverted indexes. So an inverted index is a map from words to documents. So this is, we imagine that we've downloaded lots of text documents from the web, and now we want to be able to efficiently search over those documents. So an inverted index is a map from words to documents, and it's called inverted because usually documents map to words. Like you look up a document using a URL on the web, and what you get back is a sequence of words that are within that document. So this is the opposite. You give the word and you get the document. Okay, it's an inverted index. So examples of applications of inverted indexes, well, we have a lot, right? With the web now, we have Wikipedia search, IMDb search, Google search, we have Yahoo search, Bing search, and so forth. So anywhere you see a search box where you can put in some text, there's an inverted index behind that. So inverted indexes are very important for managing text documents, text data, textual data. So we'll see some examples of flavors of inverted indexes. So we'll take this example and we'll just focus on a short snippet of the text. Retrieval Station is a 2013 American drama film written and directed by Ryan Coogler. So this is a sentence we've extracted from the Wikipedia document. We'll consider it to be a short document on its own. So we'll just call this document 1. We're going to assign a document ID to it. This could be sequentially over all documents or whatever, but we assume the documents have some IDs. So what we're going to do is effectively create an inverted index where for each term, like directed, we can say that this is contained in document ID 1, document ID 2, and so forth. Or drama is contained in document ID 1, document ID 16, and so forth. So we're essentially mapping terms or words to documents. Or in this case, web pages, for example. So if we have an example search, American drama, for example, there are some Boolean combinations that are quite common and non-Boolean combinations. So we can do and. So it would be American and drama, which would require intersecting the posting lists to find the set of documents that contain both American and drama. 1 would be one of those documents, or would require taking the union of the posting lists. We can also have phrase search, but actually phrase search right now is not possible, right, with this flavor of inverted index, because we have no information about the position of the words in the document. So we have no idea if the exact phrase American drama occurs in any of these documents. We could find the closest we can do is and, to say that, okay, both words are somewhere in the document. So how could we implement phrase? So we can't do it here. We can't answer phrase questions, phrase searches. We can't evaluate them because we have no positional information about where the word appears. So possibly the obvious solution would be to start also index for each word, the offset in which it appears. So this is maybe a little bit ugly, but we have, positional offsets of each of the words. So we see somehow where the word begins. So in terms of the inverted index, then what we're now going to be indexing would be not just the document, but the offsets in which that word appears. So the first letter of that word appears. So we say, for example, that station appears, station's not here, but 28, 20, let me see, drama. Yeah, okay, 37. It should be 37, okay. But in any case, we see that the first appearance of drama appears at character 37. This should be the same here. So it gives us the positional information about where the word appears in each document. And now we can do phrase search. We have enough information at least to be able to search by phrase. So we can see that we have different flavors of inverted index. So we have this, what's called record level inverted index, which maps words to documents without positional information. And we have word level inverted index, which additionally maps words with positional information. So it tells exactly where that word appears in the document. So there's obviously a bit of a trade-off here in that this is going to take more space, but it provides more types of searches. It's somehow more powerful for doing search. So it provides us with more features for search features later. This will be more concise, more efficient somehow, but it will only be able to solve simpler searches. Any questions or doubts? Okay, so a key concept here is that there's not just one notion of inverted index, but we can have several flavors. And we'll see a third flavor later that's somehow in between both of these. Okay, so we'll just start with these two main flavors. So the next general problem that we have to solve when we think about inverted indexes is word normalization. So the issue is that we might have searches where the terms don't exactly correspond to terms, I mean words, they don't exactly correspond to what we've indexed in our inverted index. So in our inverted index, we have a term list, which is just a list of words, and what we call the posting list, which is the list of documents, possibly with positional information where that word appears. So we have a search here, drama America, and we have the word American here. And we would probably expect that essentially America should match with American because they're very similar terms, and we would expect there to be a match. But if we don't apply any form of normalization, or if we don't somehow establish this connection between both words, then we might miss results that might otherwise be expected. So we need to consider normalization to avoid minor variations like plurals or adjective forms missing the term list in terms of what's been indexed. So how do we solve this problem? Any ideas? Okay, so we normalize the words. There's a couple of specific types of word normalization. I'm not sure if you've heard of them, but you may have heard of them in another context. So what are the options for normalizing the words? The first would be stemming. So stemming refers to cutting the ends off the words in a kind of almost dumb way, like just cutting off after a certain prefix, cutting the word and taking that word as the normalized version of the word. So in practice, this would more likely be Amérique than America. Usually you cut out also the vowel here. But in this case, we would be lowercasing and then just cutting off the end of the word after a certain point. So what this does is essentially recognizes some common variants in terms of their suffixes, like eyes, as, and things like that, and cuts them off. So this is one option. A more advanced option is to use lemmatization. And a lemma, possibly it's the same in Spanish, but it means the sort of base word, the root word of all the different forms, right? So if you think of a verb has a sort of a base notion, and then you have all these different conjugations of the verb, let's say, for example. But it's not just based on stemming. You can also recognize syntactically diverse words. For example, they can recognize that better and goodly and best are all basically the root word of all these words is good. So it requires some knowledge of the language beyond, common suffixes. It requires some more deep linguistic information to function correctly. Another element, so I would say in general that lemmatization would replace stemming. So if you have something that can do lemmatization, that's probably better than stemming, but you need that for every language that you support. So for a specific language, at least they would. But another thing that can complement both would be synonyms expansion, which would be this idea of saying, for example, film and movie, they both refer to movie. So that way, all these terms here will be matched against this sort of normalized word here. So how does the normalization work? So first of all, it's largely language specific. So stemming rules can maybe sometimes manage European languages. You know, you can have a general. So the difference between synonym and limitization. So the idea would be in limitization, you're finding the base word. You're finding the word from which the others derive. So your base word could be, for example, a verb, go. And then all of the variations of go, going, went, will go. So it's not so easy in English as it is in Spanish, but you have all these different variations of go. They're just different conjugations, tenses, plurals, agreements. And it knows that all of those are just forms of go, basically, right? So it gets rid of things like plurals. It gets rid of things like adjective forms. It gets rid of things like conjugations of verbs and recognizes that the core, what the base word is, that's the lemma. It's sort of the base word from which all these other variations derive. Synonyms is a bit different in that the lemma of film would still be film and the lemma of movie would still be movie. They don't derive from the same base word. It's just that they have the same meaning. So in this case, these are synonyms, but they're not related by lemmas. So a lemmatization of film and movie would probably be film and movie, but the synonyms will recognize that they mean pretty much the same thing. I mean, there are some differences, right? Film can also refer to the physical film on which movies are recorded, but for the example, this is quite reasonable, let's say. Hopefully it's clear, the difference between synonym and lemmatization. Okay. So we can take okay, so I've spoken longer than I meant to, but we can take a break in a couple of minutes at 3:15. So this is language specific. So stemming is the least language specific, and probably synonym expansion will be the most language specific. So you need some knowledge, some linguistic knowledge to be able to effectively normalize words. Once you have a normalization, which is sort of this idea of mapping multiple words to one normalized form, you need to use the same normalization on the query and the document. If you use different forms of normalization on the query and then later in the documents, when you build the inverted index, your normalized forms won't correspond. So if you use one type of normalization here in the query and use a different type of normalization to build your term list, you could still end up with mismatches between what's the normalized form of your search and the normalized form of your term list. Okay. So we can take a break there. I think I should have stopped at 3:10, but we can take a break from 3:15 to 3:25. Any questions or doubts? Okay, so break until 15:15. Oh no, from 15:15 to 15:25. Okay, so we spoke about normalization of words. So next we have to consider the space. Okay, so how large will these inverted indexes be in terms of the number of entries that they have? So there's two elements. There's first of all the length of the term list, and there's then the length of the posting list. But we could actually just count how many entries there are in all of the posting lists, as it will be essentially, this is the dominating factor, we could say, in terms of asymptotic analysis. So what would the space be in the record level? How could we express that? So how many entries do we have here? So we could express that in the following way. We could say that it's the sum of unique words in all documents. So we take the count of unique words in each document, which we'll define as U, and then we sum that for all of the documents in their collection D. So for all the documents in our collection D, take the number of unique documents and sum it over all documents. So here, the number of elements in our posting list should be equal to the sum of unique words in all documents. What about in the case of the word level inverted index? So this time we have the positional information, right? So it would be equivalent this time to the sum of the non-unique words, or the number of word occurrences in all documents. So the word count according to Microsoft Word or whatever. So the sum of all word occurrences or non-unique words in all documents. Every time a word appears, we are going to have an entry here in our posting list. So this is in terms of the uncompressed, or the raw number of elements that we need to store in the posting list. So in terms of unique words, we mentioned before about how we have this heaps law, where the number of unique words in general is somehow proportional to a constant times an exponential number. So what is k and what is beta here? These are essentially, let's say beta is a factor between 0 and 1, less than 1. So it's sort of like an exponential decay, and k is a constant factor. So we have here a plot of the number of words in text. This is from Wikipedia, and the number of unique words in the text. So as we advance reading more and more word occurrences, non-unique words in a document, we're going to find many unique words at the start, and then we're going to see more and more repetitions, leading to a sort of slower growth in the number of unique words in the text. So looking at an example, in English text, our constant is sometimes estimated to be between 10 and 100. And beta, this exponent here, is estimated between 0.4 and 0.6. And with this, we should be able to fit more or less English text. So for example, if we go here, we have 600,000. So we should expect 600,000 to be roughly proportional to some constant factor between 10 and 100. If we insert 10 times 600,000 to beta in the interval of 0.4 to 0.6, we'll put 0.5, and we get 7,740, which is roughly actually what we see here. So at least for this data point, I didn't actually fit the entire curve, but at least at this data point, it fits with beta equals 0.5 and k equals to 10 for English. So what's the main point here? Even in very large collections of text, there is a sort of an asymptotic bound on the number of unique words that we're going to find. So after a while, the unique words, we'll see all the common words in English, and then we'll just start finding, proper nouns, names of places, names of people. And even still, there aren't that many unique names of people, names of places, and so forth. So we're going to start to run out of unique words, or we'll have seen all of the unique words, or most of them, a great majority after a certain point. So if we take this into account, then, and we consider again the space, what sort of effect does it have? Well, the thing is here that we're doing the sum of unique words in documents per each document, which means that we have to be maybe a little bit careful in the sense that this factor only applies within a particular document. So it means that if we have very large documents, then this will be much, much smaller. Yeah. But if then the word level inverted index, but if we have relatively short documents, like we're indexing tweets, for example, then intuitively we could actually expect that the space here to be more or less proportional between the record level and the word level inverted index. So the difference between both will be greater the longer on average our documents are. Okay. So we also have an issue when we consider space and efficiency of the common words in the inverted index, where we have this phenomenon of there being many occurrences of few words and few occurrences of many words. So if we look at English, for example, or this applies to many languages, we have Zipf's law. And Zipf's law specifically states that the most popular word will occur twice as often as the second most popular word, 3 times as often as the third most popular word, and in general, n times as often as the n most popular word. Of course, this is this generates a distribution, and this is sort of an approximate distribution for the occurrences of words. So if we look at English text, we see that this corresponds pretty well to Zipf's law. So 7% of the word occurrences in English text will be the. 3.5% will be off, and we would expect this to be half the number of occurrences, which is actually what we see. And third comes in with and with 2.7%, which again is roughly 1/3 of 7%. So we see that this fits actually pretty well to Zipf's law. In languages such as Spanish, where articles are gendered, there might be some differences here because you have this split between la, el, these sorts of things. But in general, in English as well, sorry, this means that this corresponds to that 135 words cover half of all occurrences. And there's something similar in all languages. So if you could learn about 100, 200 words in a given language, you should be able to recognize half the words in a particular text. So Wikipedia gives this graph again of different distributions of languages plotted according to what we would expect with Zipf's law, where we would expect this to be a straight line. So we see that there's some, some variations at the start, and there's some variations at the end, depending on how extensive the vocabulary is. But we see that they largely follow, in general, this sort of Zipf's law. So what this means is we have to take into account that there will be a small number of words that will appear very frequently. So this means that we can expect some very long posting lists for common words, and we need to maybe think about how to cater or how to optimize for these, how to handle them. So one option would be to implement stop words, where we just say we don't care about common words. Because they're so common, they're not informative. Like the in a search is just not useful. So somehow the most common words contain the least information. So we can drop words like the and in, for example, as they don't really help so much in terms of narrowing down the search. Another option might be to implement record level or block level addressing. So block addressing is this idea, it's somewhere in between the word level and the record level indexes that we saw earlier, where we divide our documents into blocks. So the blocks can be of whatever size. It's a variable length. It's a parameter then of our inverted index. Where we then index, rather than having exact positional information or only that the word appears in a document, we can say that a word appears in a block. So this is our new positional information. It's not an exact position, but it's just that it appears in a given block of text. And what this allows us to do is, if we have repetitions of very common words in a block, okay, maybe your blocks might be much larger than 10 words. Maybe you have it for paragraphs or for 1,000 words, whatever it may be. This will allow you to somehow compress a bit the number of occurrences that you need to store in your posting list. So it gives us sort of a parameter that allows you to vary continuously between a word level index and a record level index. And this would also help you to address common words by essentially the fact that if you have larger blocks, you can remove some of the repetitions of common words. Okay, so what is the effect on phrase search? If we don't have exact positional information on words, but we can do a sort of an approximate phrase search if we have small blocks. So if we have very small blocks, maybe like we see here, then this might be pretty okay. But if we have big blocks, then that would not be so great. This has another benefit, which is that we'll have smaller numbers as well. We'll end up with, rather than, having to remember every exact position in the document, we'll have fewer kind of numbers or values here, which will be better for compression. But okay, for phrase search, small blocks would be okay. Big blocks would not be okay. So again, we have this trade-off between how expressive are the types of searches that we can do accurately and the overall space and efficiency of the inverted index. So returning to this, we can expect long posting lists for common words, but the flip side is that we could also expect more queries with common words. So we could also expect there to be a lot of queries for words that are commonly found, much like, I don't know if there's some proof of this, but it's like the words you will commonly find in the documents will also be commonly searched for. There seems to be a trend along these lines. But what is known is that there is a long tail of search. So this means that the more generic queries are often encountered, whereas very specific queries or searches are rarely found. And one example of this would be, for example, the search coffee appears quite a lot in a search log, but something like medium roast coffee beans vacuum pack is not going to be searched very frequently at all. And in fact, there's this long tail where actually the volume here under this long tail at some stage is equal to the volume here. So what this means is that there's a certain, your log is sort of split into very frequent queries and a small number of very frequent searches that are very frequently searched for, and many searches that are rarely searched for. So this kind of catering to the long tail of searches is also important because it has a large volume of the overall searches. So this is called a long tail of search. How do we optimize for this? Any ideas? And as a hint, we're mainly optimizing for this part here, for actually the common volume of common searches that are repeated very, very often, like coffee. So if we're getting a lot of searches for coffee, what could we do? If we're getting a search for coffee every 5 seconds, it probably doesn't make sense to recompute the search every time. We could just remember the results of the last time there was a search. So we could consider using caching techniques. So we can just remember the results that we computed the last time. Obviously, at some point, we'd have to invalidate or refresh the cache. But in general, the concept of caching the results so that we can reuse them several times seems to make a lot of sense for optimizing for this traffic here, the very common searches. Okay, so these are some common techniques, and these sorts of techniques that I spoke about before are why Google works so well in terms of volume of searches and amount of documents that are indexed. These principles or these laws that we saw in terms of the distributions of words, the distributions of queries and so forth, the ability to perform caching. These all sort of enable the sort of scalability of search engines such as Google. There aren't that many unique words that need to be catered for. Certain searches will be very, very common and so forth. So aside from that, we also need some efficient data structures. So we need to actually implement the inverted index using some sort of data structures. And we have some options for that. So mainly we're searching on the vocabulary keys, which is the term list, right? So what we can do in terms of the term list, the keys that we use in the term list, the words, we can apply hashing, which is fine. We can do O1 lookups if we have an ideal hash function, but that doesn't generate collisions. So that would be, as efficient as you can get, assuming your sort of ideal hashing. But we won't be able to do any range queries. So the words won't be sorted, which means that we won't be able to find all words that start with a given prefix, for example. We could try to think about sorting, having a sorted posting list that allows us to do binary search sorted term list, which allows us to do binary search in the term list, given some words from the search. And this would give us log U lookups for U, the length of the term list or the number of unique words in the index. And this would allow us to have range queries. So maybe for a slight trade-off in asymptotic performance, we have some wildcards. We can do find words, documents containing words that start with AB, for example. Another option is to try to use the fact that that in general we have a fixed alphabet. We're going to assume something like an ASCII or an extended ASCII character set. So we have a fixed alphabet, and the words that we're looking for in general are not long. They're not long strings in that alphabet. Probably on average about 4 characters per word. So we can use tries for this, which will allow us to have range queries and also provide some natural form of compression of the term list. So have you seen a try before? Or you know what tries are? So in case you haven't seen tries before, how does a try look like? It's basically a tree where you have pointers between you can form essentially strings or sequences, and you reuse the common prefixes of the sequences that you want to store, like the strings. So here we have a root element, and then we have A, G, E, and T. The word agent is spelled out here, and when we go to index and go, we can follow the common prefix of AG and then add O. So here the orange as well indicates the end. So AGE is also a word here. So somehow we indicate also the terminals, the things that end the word. So AGE and AGENT are words. AGO, ALE, BABY, BAC, KS, BE, BED. So we see how we can represent data, and then here we have how many elements, how many children can each have. This would be bounded by the number of symbols in our alphabet. So if we consider, I don't know, 50 symbols in our alphabet, 50 letters in the alphabet, then we would have to be able to search within this and find, for example, if our word starts with B, find the subtree or subtry that has B, and then again, this can have 50 elements. So we can navigate this way. And at the end of this, then when we have a word, this word can be associated with the posting list. They can point to the posting list elsewhere. It could be point to the posting list on disk, for example. So to read a word, we need to read the length of the word. And considering that the alphabet is fixed, it's a constant, so we don't care about that in the asymptotic analysis. Okay, so this is a common way as well in which we could consider using in general the idea of prefix indexing, prefix-based indexing. We can compress the data and provide efficient lookups. So in general, when we think about memory and storing the data on a machine, the term list will often be small, which will mean that because we have few unique words, which will mean that we can often fit this in memory, and we can do our searches on our try, on our hash dictionary, hash map, whatever it is, or our sorted structure using binary search. We can store this in memory. On the other hand, the posting list will tend to be larger because it kind of scales linearly with the number of documents or the amount of content we have. So in general, we'll often store this on disk, and we might end up caching certain hot regions, like the posting list for terms that are frequently encountered, for example. We might be caching them in memory. This would be a typical configuration for an inverted index. So term list is in memory, contains all the unique words, all the unique terms, and then it allows us to very quickly in memory find the location of the posting list on disk, and we can read that then from the disk. Of course, if you could fit everything in memory, that would also be great, right? So that would make everything even more efficient. So another important thing in terms of memory to allow us to store, for example, more data in memory as well, is to use compression techniques. So in general, compression techniques here, the most important techniques relate to numeric compression. So why is this? It's because typically we're not going to, in our posting list, write the full URLs of the documents, but rather we're going to have a dictionary that stores document IDs. So our document IDs are going to be numeric, and then later we can, from another dictionary, get the URL of the document. So numeric compression is important because we have posting lists, and posting lists tend to be lists of numbers. So if we can use numeric compression, we can reduce, and we're mostly preoccupied with the, worried about the posting list, because this will in general be the largest part of the inverted index. So numeric compression is important. There are some numeric compression techniques we can apply. The first is called interval indexing, which here we'll see an example for record level indexing, but it could be applied for whatever list of numbers we have. It could be block level indexing or for positional indexing or whatever. So we have our raw posting list here, and the idea would be intuitively, okay, we have an interval 1, 2, 3, 4. So rather than storing 1, 2, 3, 4, we can store an interval 1 to 4. So here we have another interval 6 to 7 and so forth. So we can store the list of numbers like this. If we assume we have a relatively dense list of numbers, we can also try to be super clever and try to group similar documents together so that they have similar document IDs. For example, documents about countries in general in Wikipedia, we can try to give them a sequential list of IDs so that the intervals become smaller. So we can optimize even further by assigning the document IDs in a sequentially intelligent way. So this is one option. Another option is to apply gap indexing, where the idea is rather than indexing intervals, what we're going to do is we're going to index the gaps between countries. So in this case, instead of 1, 3, 4, what we're going to index is our base number, our base value, which is 1, and then the difference. So we're going to say 3 minus 1 is 2, or 2 plus 1 is 3, 1 plus 2 is 4, 4 plus 1 is 8, 1 plus 4 is 1 plus 8 is 9, right? So we just index the intervals, and we can get the real values by just summing along the sequence. Okay, so this is a bit weird. Gap indexing, because I promised that this would be a compression technique, but we see we have 5 numbers here and we have 5 numbers here, right? So we need 1 number for each number here, right? So where's the compression? So any ideas of why this is a good idea, or why gap indexing is useful? Yeah, so the smaller numbers definitely help. Yeah, there is another aspect aside from the smaller numbers. And the idea of whether to use shorts or ints or longs, actually, we'll come to that in a second as well. But the small numbers will help us compress further. Anything else? Yeah. So we have more repeated values. Here we can't have any repeated values because this is a record level indexing and it doesn't make sense to have the same document twice. Here we can have repeated values, and that means that they can be compressed based on the frequency in which they appear, for example. So we have repeated values and we have smaller numbers. So this is sort of like, it's not a compression technique in itself, but it's almost like a pre-compression technique that can help with other forms of compression. So repeated smaller numbers will be easier to compress. In terms of compressing the numbers themselves, the typical way we represent numbers is by using fixed byte size numbers, like we have shorts or we have integers or we have longs. This is obviously a bit wasteful in the sense that, okay, it's the best way that we could store numbers that are randomly distributed in that binary interval, right? But typically we're not going to have a random distribution of numbers, and typically, we might not have a fixed bound on the max size of a number. So a neat way to be able to compress numbers is to apply bit level techniques, where we use variable length coding. So how this works is we're not going to assign 2 bytes, 1 byte, or anything like that to a number, but rather we're going to try to assign it so that in general lower numbers or more common numbers will be assigned shorter codes. So an example of this is the Elias gamma encoding, which assumes many small numbers. So we can use this to encode any number. There's no limit on what integers to encode. So we see here we have our input number. And this can be adjusted. So we could add a 100 to it. So 101, if it's a very common number, somehow becomes the 1 here, right? Whatever, you know, or this could be 0 as well. You know, you can shift this in the, you can shift Z obviously to whatever is most useful. So anyways, let's assume it's 1. So this is the base case. So the first thing you're going to encode is the base 2 of this number. But you're going to floor the base 2 and you're going to encode that in unary. So 1 gets 0, but then 2, 3 gets 1, and then 4, 5, 6, 7 gets 2, and then it goes up in the power of 2. When you escalate a power of 2, you add a 1 here to encode somehow the log of 2. So the next time it will go up will be 8, 16 will have 4, 32 will have 5 ones, 64 will have 6, and so forth. We need to end the unary number. So this sort of encodes the power of 2 in which we're in. We need to encode a 0 to end the unary number. Otherwise, the unary number doesn't really make sense. So we need to stop the unary number with a 0. Unary again, meaning just, you know, 1, 1, 1. So to encode n in unary, you give 1 n times. A 0 to end the unary number, and then what you're left with is the remainder. Okay, so from this, it kind of gives you the power of 2 that you're in. And then here you encode the remainder. So for 46, you would encode the power of 2 is 32 here. And then you need to encode what's left, 14, right? So 46 minus 32 is 14. You need to encode what's left after the power of 2. And you do that in regular binary, right? So you can use n bits here to encode the remainder. And then that's your final Elias encoding is the concatenation of these 3 things. So 4, since it's a power of 1, will end in a bunch of 0. So it'll be 1, 1, 0 to end the unary, and then 0, 0 because it has no remainder. 5 will be 1, 1, 0, 0, 1, adding a remainder. 6 will be 1, 1, 0, 1, 0 in this way. So this gives us a way to compress numbers without fixing the size of each number, like saying, okay, we're storing integers, we're storing longs, we're storing shorts, right? So you end up using more bits. It depends. It depends on the distribution of your number. So we'll come back to that. We'll come back to that. So yeah, this is not like you're not beating entropy or anything like that. But if you have a lot of numbers, like you apply your gap level, your gap indexing, and you have a lot of numbers like 0, 1, 2, 3, 4, this can definitely help. But we'll come back to that. The distribution is important. Yeah. So this is one scheme. So we can try to take an example. Anyone want to decode 0, 1, 0, 0, 0, 1, 1, 0? So could we decode this into a sequence of numbers? So what would be the first number? First number would be 1, right? So that's the 0 gone. What about 1, 0, 0? So we've done this one, okay? What about 1, 0, 0, 0 or 1, 0, 0? So we see that since it's a 1, it's a power of 2 is just 1. So it's 2 or 3. And then we have the 0, right? That ends the power of 1. And then we have the 0, which says no remainder. So it's 2. Okay. What about 0? 0 has to be 1. 0 has to be 1. 1, 1, 0 means it's 4, 5, 6, or 7. And then the remainder is 0. So we know it's 4. Okay. 1, 1, 1 means it's now 8, 9, 10, 11, 12, and so forth. And the remainder is 0. So that's 8. And we have 1, 1, 0, 1, which is 5. Okay. So we have 1211485. Okay, so our next type of encoding is delta encoding, which is very similar to the previous thing, but how about instead of using unary to encode the power of 2, what about if we use Elias gamma sort of recursively to encode this, right? So what if we use this scheme here to encode this part here rather than encode it in unary? So this is the idea of the Elias delta encoding, which has this sort of recursive element where now the power of 2, we don't need the separator 0. It's not going to be encoded in unary. It's going to be encoded in the previous codification. Okay. So that's the idea. And we get the power of 2 here. And then we just encode the remainder in the same way. And this gives us the Elias delta encoding, which can be better for some distributions. So you can look at how to decode this later, but you can convince yourself that you can decode it, right? So and the space is here in terms of how many bits you need for a given integer. So the previous methods are non-parametric, but there are other compression techniques that take a parameter, a value. For example, there's a column n encoding. So we can have a column 3 code, which is quite simple compared to the other ones. Pointer arrow. What we do is if we have a column 3 code, we divide the number by 3. We sort of give the multiple of 3. So 1, 2, 3 will be 0, 4, 5, 6 will be 1, 7, 8, 9 will be 2, 10, 11, 12 will be 3, and we encode that number in unary. This is sort of the multiple of 3 that we're in. So we encode it with unary, which has the 0 separator at the end, and then we encode the remainder. And here we need 2. In the case of 3, we would need a remainder with 1 or 2 bits for this. So in general, here we see the final column 3 code. So we encode the sort of multiple of 3, and after that, just the remainder, the 1, 2, 3 remainder. So this gives us column 3 codes. So which is better, which is worse, right? We can do it analytically, and the analysis is actually in the slides. You saw the space analysis. But if we just look at some examples, it will become a lot clearer. So if we look at small values where we have lots of integers between 1 and 8, then what we'll find effectively is that in general, column 3 seems to work better. Like for example, when we reach 8, we see that we have 5 bits here versus 8 or 7 bits here and 8 bits here. Okay, so we see that column 3 codes seem to be doing well for very small numbers. But if we look at larger values, without going to very large values even, right? But if we look at larger values, we see now that the delta encoding is more compressed than the gamma encoding. And column 3, how many ones do we need here for column 3? So you see this dot, dot, dot. So we need to encode in unary the multiple of 3 that we have. So what we would need to have is 33 ones here. Followed by the remainder. Okay, so in general, this will be 35 digits or bits long, right? So this will be much longer when we get to larger values. So it depends on the distribution of values that we have, and we're kind of assuming, so you can choose the sort of type of codification, the type of encoding that would be best for the distribution of values that you would typically see. I have just 1 more minute left. I have also 1 more minute left in the class. So the last thing is that we can use variable byte length codes. So what this means is essentially if we have a sequence of numbers, we can just use the last bit of byte to indicate if the number ends. So it allows to encode run-on numbers. So in this case, we indicate that we'll assume 0 indicates the end of a number. So here we encode 1 number, here we encode another number. Here we use 1 to say that the number continues. So we can use this for variable length, but byte level variable length numbers. At the cost, again, of course, of using the bit here to indicate run-on or not. So this is 18 based on this value here. This will be 81 based on this binary value here. And this will take the concatenation of the first 7 bits here and the first 7 bits here, 14-bit number, in this case representing 274. So there are various techniques for how to compress sequences of numbers. Okay. So some other optimizations that we can consider, we can order posting lists to give the top documents first. You know, if you have some very popular documents that are relevant, we can try to pre-order the documents to be early in the posting list. We can try to somehow apply selectivity. Like if we have a join between one rare word and one common word, we start with the rare word and to reduce the possible results. Distribute over multiple machines, which we spoke about. Actually, we didn't. So we'll have to speak about that. So in general, with these optimizations, it becomes very efficient to index inverted indexes. There's just a tiny bit left in the class, but it's over time. So I think I'll finish. Rather than to go through it very quickly, I forgot about this part. We can finish in the class on Wednesday, but there's not much left. Any questions or doubts? Or does it make sense? All good. So the specific compression techniques, I mean, there's lots of different compression techniques. I think it's interesting just to get some ideas on how inverted indexes can use these sorts of compression. But you know, there's a lot more details. There's lots of other different types of compression that could be done. Gonzalo Navarro works a lot on compressed data structures, which goes more into terms of how to combine compression with efficient lookups. And the other thing is efficient intersections of posting lists, which is the sort of problem that Gonzalo and Jeremy have worked on. So, yep. So there's a lot more depth to this, but I think it's good to have some ideas of bit level compression, byte level variable length compression, and encoding, and so forth. So these sorts of elements lead to inverted indexes being very scalable and efficient, and leading to the fact that it's feasible to have applications like Google and Wikipedia and IMDb and so forth. Questions or comments? Okay, if not, see you in the lab on Wednesday. We're going to play with a tool called Elasticsearch. Sorry if you're going slightly over time. I thought I could finish, but I forgot about the distributed part. See you on Wednesday.
Ciao.
Bye.
Ciao, ciao. Bye.
Chao, chao, profe.
Ciao, profe.
Ciao.
Ciao, profe.